have a seat right there. I'm going to introduce you. Ready? Okay. Good morning. I think we're going to get started. And actually, we have I want to welcome you to the Chairman's Air Pollution Seminar Series. We actually have a pair of seminars today from our investigators from the Southern California Particle Center and Supersite. In fact, we have both the director and deputy director, Dr. John Freunds and Dr. Kostas Tsioutis. Our first seminar this morning will be from Dr. Kostas Tsioutis on some of the research findings of particulate matter-related toxicity from the Supersite and the Particle Center. First, to introduce Dr. Tsioutis, who comes to us from Greece, that originally got his bachelor's degree at University of Thessalonica. He's left sunny Greece for the United States. Went to the University of Minnesota to receive his master's degrees and two master's degrees in engineering, aerospace engineering, mechanical engineering, and then went to Harvard University where he received his PhD in environmental engineering. That currently, Dr. Tsioutis is an associate professor of civil and environmental engineering, as well as the deputy director of the Southern California Particle Center and Supersite. He also is focusing his research on characterization of air pollution, especially particulate air pollution, where he has a focus on developing new monitoring technologies for particulate matter, fine and ultrafine pollutants. And through that capacity, he served on our Air Quality Advisory Committee for the review of the particulate matter standards that were completed in 2002. So with that, I'd like to introduce Dr. Kostas Tsioutis.
Thanks, Rich. Thank you very much, and thank you all for inviting us today to this seminar. Originally the plan was to have Dr. Freunds give the 11 to 12 seminar, and I was going to give the afternoon seminar. But after we both reviewed our slides, we realized that it made a little more sense to first cover a few things, some of the results in the areas of atmospheric measurements, as well as the development of instrumentation. That all of these results were generated through our Particle Center and Supersite. And then in the afternoon, Dr. Freunds will talk about health effects and implications of all of these findings today from this research effort. So one of the things that I'm going to focus on today would be ultrafine PM. I will present to you, of course, PM characteristics and physical and chemical measurements of all different sizes, but you will see that some of the things that are, in our view, particularly interesting and novel is our research on ultrafine PM, which, as we will explain later by Dr. Freunds, are of substantial toxicological importance. And the more we know them, the more we have reasons to believe that one has to keep a closer eye on this PM. So I'm going to talk to you today about what we have found so far with regards to sources and formation mechanisms of particles in our basin. What do you know about the way their properties change diurnally, seasonally, as well as within different locations of our basin. And I'll also describe some of the technologies that are developed to study physical, chemical, and toxicological properties of these particles. This is a graph that I took out of a textbook that portrays size distributions of PM expressed based on number as well as volume or mass concentrations. With respect to number concentrations, the atmospheric aerosol is primarily, if not exclusively, dominated by particles below 0.1 or so micrometers in size, which is the particles that we refer to as ultrafine PM. Some people in the literature choose to refer to this, to sort of the larger end of the ultrafine mode as Aitken nuclei, and the smaller end of these particles of the nucleation mode. The distinction between the two being that these particles, especially the particles below 10 nanometers, are extremely volatile. They're products of essentially condensation of vapors to become particles, whereas these the Aitken nuclei are somewhat grown by diffusion ultrafine PM. If one portrays ambient distributions weighing every particle by volume, then we will see that basically the contribution of this mode disappears, and we have two other modes, an accumulation mode and a coarse mode. Coarse mode defined roughly between 20, 30 micrometers, and the accumulation mode defined roughly between 0.1 to 2 microns. There are some subcategories even within the accumulation mode that one might observe in Los Angeles more than other areas. There is a sort of a condensation submode. It's this area right here between, I would say, 0.2, 0.3 microns and so forth, which is a sort of a grown ultrafine mode. These are particles that are formed by gas-to-particle conversion processes. And then there is a somewhat larger mode right here that you see, which is called the droplet mode, primarily consisting of PM of hygroscopic constituents such as sulfate and nitrate and some polar organics that they grow by mostly because of by hydration and as well as by aqueous reactions in the liquid phase. We've been very fortunate to do our research in Los Angeles, which is probably the closest thing, at least in the United States, that you've ever seen with respect to an ideal real-world laboratory. We have predictable, reproducible, very consistent meteorology. We have very consistent wind patterns, and that has allowed not just us, but even investigators that preceded us, like the people with the SCAC studies and other studies that took place in the basin, to treat this whole area as one big laboratory where there is distinct sources and distinct receptor sites. And that has allowed us also, these distinct sources affect differentially the chemical composition, the chemical properties of particulate matter in these different sites, and that has enabled us to do hypothesis-driven toxicology studies focusing on the chemical properties of PM. Within the context of our center, we have conducted research into sort of three areas that are distinctly different from each other with respect to PM sources. If we have areas that are impacted immediately by freeways and busy streets, you will see later on in my talk, what the zone of influence may be and how it is defined in terms of actual distance. We have then areas that are more reflective of a typical urban aerosol, areas, in other words, that the aerosol is still fresh, but it's not directly coming from a freeway. It's a little more mixed and dispersed. And then we have areas in the inland valleys of Los Angeles whereby the aerosol is advected after long-range transport and gets there after anywhere from 10 to 20 hours of residence time in the atmosphere. And in the process, depending on the season, you may also have photochemical reactions modifying the composition of this aerosol. So this is basically the red arrow right here is the predominant wind trajectory in LA. This is some of the sites that we call source sites, USC, Ball Heights, and then San Dimas, Upland, Claremont, Riverside. As we move eastward, this is what we call our receptor areas. And in each one of our sites, and this is a sort of a timetable of what we have done and where we are right now, through the center and the Supersite, we've done continuous and time-integrated physicochemical measurements of PM properties, and concurrently to these measurements, we have conducted in vivo and in vitro studies to concentrated particles, to CAPs. I'm going to go, there is a lot of information, and most of you will notice later on that in every single one of the transparencies and slides that I show, there is a reference like this, or there is an author in a paper. So if you need more information, I can refer to you to the appropriate publication. So I'm just going to give you almost a summary of our results. But this is the monthly average chemical composition of ultrafine PM in our basin, starting in late 2000 in Downey, and then covering the Riverside, Rubidoux area, Claremont, and currently at USC. The different components here. This is elemental carbon, organic carbon, metals, sulfate, and nitrate. And one of the things that you notice is that basically source sites such as USC and Downey have somewhat higher concentrations of ultrafine than receptor sites. The concentrations in source sites, as you can see here, they actually increase as you go from the fall to winter, so as we move towards the cooler season. The concentrations, by contrast, in receptor areas, for example, in Claremont, you see that they actually follow an opposite temporal trend. They actually increase as we move from the winter to the summer, to some degree because of there is more long-range transport and advection from downtown LA, but there is also the effect of photochemistry that produces a fair amount of these particles in the receptor areas. Organic carbon is by far, no matter where you are, the most important or predominant constituent of ultrafine PM. What is not organic carbon is elemental carbon, and depending on where we are, you might also see metals playing, between 10 to 15% by mass of ultrafines. This is the distribution by size and site of organic carbon. Organic and elemental carbon are actually of particular interest to our center because a lot of our toxicology studies focus on organics. The organic carbon is, the majority of it is in the accumulation mode. It follows very similar trends in terms of its seasonal variation to the ultrafine mode. In other words, you see more organic carbon in the source sites, increasing in the winter. In the receptor areas, you see more in the summer, a decrease in the winter, and then more again in the summer because of advection and more material, more PM being advected from source to receptor areas, and also because of the effect of photochemistry. This is actually an interesting slide because it's elemental carbon and partitioned in three size modes, ultrafine, accumulation, and coarse PM. And one of the things that you're going to see, of course, is that, perhaps with the exception of Riverside, there is probably more elemental carbon in the source and receptor sites. But what is of particular interest is that, when you see, for example, receptor sites, you see that elemental carbon actually increases during the warmer part of the year, then decreases in the winter, and it increases again in the summer. And this is a completely counterintuitive result. I mean, elemental carbon, there is no, to the best of our knowledge anyways, there is no photochemical mechanisms that produce elemental carbon. This is all combustion. You would think that combustion products would be higher in the winter because of the compressed mixing depth of the atmosphere. And this is, in fact, something that you see in in the source sites like Downey and for the most part USC. But this is not something that we see in our receptor sites. And this increased concentrations in the summertime, which again are counterintuitive because that's the time of the year that the mixing depth of the atmosphere increases, is basically a signature of long-range transport of elemental carbon from the much more polluted urban areas of Los Angeles into the downwind receptor areas of our basin. The particles tend to be much smaller in source sites. This is a chemically speciated, size fractionated PM10 composition in Downey. Starting from the ultrafine mode and going all the way to coarse PM, you see, basically what we covered in the previous transparencies, a mass meter diameter of about 0.35 microns. As the particles get smaller, we have more elemental and organic carbon. As the particles get bigger, we have a little more nitrate, sulfate, and of course, in the coarser PM, we have an abundance of trace elements and metals, mostly reflective of paved road and paved road dust and crustal material. Now, when you go to receptor areas, while the chemical composition doesn't vary all that much, although we do have more nitrate, of course, in Riverside because of the formation, because of the ammonia sources that precede by a few miles that area. We see that basically the MMD, the mass meter diameter of the aerosol, is almost double that of Downey, which is again a sign of long-range transport and advection that favors particle growth. So particles tend to be bigger actually as you move inland than the freshly emitted urban aerosol of LA. This is another way of saying the same thing now, looking at a specific composition of PAHs. This is a plot of PAHs starting from fluoranthene right here all the way to indenopyrene. This PAH they become more and more volatile as we move to the left of that axis and less volatile as you go in this direction. And what you notice here is that at Downey, basically most if not all of the PAHs, the majority of them is in the ultrafine mode. By comparison, in Riverside, you see that this PAH is now increased, and they find themselves partitioned mostly in the accumulation mode. So we have again growth to a larger size as a sign of, or as a result of long-range transport and advection. This is data, also pH data in Claremont, another receptor site, now broken down by two different groups, from phenanthrene to fluoranthine and benzoanthracene to denylpyrene. This first, this first group is actually somewhat more volatile, and these are less volatile PAHs. Again, these are fractionated by size and also by season. And some of the things that you hear is that, first of all, in no matter what time of the year we are, and no matter what kind of PAHs, whether less or more volatile, the majority of these PAHs is in the accumulation mode, considering that Claremont is a receptor site, as you would expect. With the only exception of this month right here that I have with an arrow, which is February of 2002, that we had very strong Santa Ana conditions. The wind reversed itself, was blowing from the deserts, and so that's somewhat of an odd data point here, but we felt that it's constructive, to say the least, to include it. What else we see? We see here that no matter, especially in the more volatile or high volatility PAHs, we see more coarse PAHs, or we see PAHs actually partitioned in the coarse mode, whereas we see very little of these PAHs partitioned in the coarse mode in the lower volatility compounds. We also see that the coarse PAHs increase as we move towards the warmer season, which is a direct result of volatilization of PAHs from it's a result of actually having more PAHs in the gas phase in the summertime. These PAHs then see a much bigger surface area of coarse particles. They adsorb onto them, and this is basically the result of it. So we have more PAHs in the more volatile PAHs in the warmer months in the coarse mode, whereas we barely see anything in the lower volatility PAHs. These PAHs, the higher volatility PAHs, also increase somewhat counterintuitively. Their concentration increases as we go from the colder to the warmer season, whereas the lower volatility PAHs actually decreases as you go from the winter to summer, as you can see here. And they're both results that are expected. Now, a little more focus. Besides, this is diurnal plots of elemental carbon, ultrafine mass, and ultrafine number at USC average between November and February of this last year. USC is a source site, and basically what you see here is a clear signal of vehicular emissions. You see that the diurnal peak of these distributions that match very well with each other. They actually track each other very well, rather. It's somewhere in the 8 to 10 in the morning time period, and then they sort of tend to go down as the traffic decreases and the mixing depth of the atmosphere increases. This is size distributions at USC, typical size distributions of PM by numbers, with the exception of maybe midnight, which is this light blue graph that you see right here, where we see the median diameter being somewhere in the 90 to 100 nanometer range. We see that the rest of the day, these plots look very similar. We have a peak around 30 to 40 nanometers, and things go up and down with traffic, basically. Evening and morning traffic are the two curves that actually have the higher concentrations. By comparison, Riverside, which is a receptor site, this is diurnal plots of elemental carbon, of particle mass and particle numbers in the red line in January and July. I mean, two distinctly different months. In January, you see that basically the peaks in the particle distributions happen during the morning and in the evening hours, as you would expect, relatively close to the traffic hours. In the summer, in the summertime, this morning traffic peak is barely perceptible here, but what you see actually here is a peak in the middle of the afternoon, which, as we're going to talk later on, is reflective of the contribution of photochemical activity and secondary formation of PM. This secondary formation wasn't just observed in Riverside, but it was also observed in Glendora, Claremont, and Riverside. Here, these are three graphs combined in one. That's July of 2002, and you see that the peaks here in these three sites more or less occur in the same time, sometime in the afternoon. And that's extremely important in the following sense. If we assume that ultrafine particles are toxicologically interesting, and as Dr. Freund will show you later on they are, in addition to the general perception of ultrafine being emitted by vehicular emissions, and therefore they have a very strong spatial variability and very sort of local strong character, There is also what I call a regional character, and these concentrations and size distributions are very, very similar in 3 receptor areas of our basin. Both numbers and diurnal trends are very similar, which we would expect if the mechanism that puts out these particles is photochemistry, a more regionally dispersed mechanism than vehicular emissions. And that's very important to keep in mind because it has important implications in terms of personal exposure. This is an average size of the particles as a function of time of day in receptor areas, starting from midnight to midnight, and this is going from February to March, April, May. One of the things that you see is that in receptor areas, the average particle size grows as the season progresses from winter to summer because of long-range transport and advection. You can see that clearly here, that the average particle size almost doubles as you go from February to May. And then in the middle of the afternoon here, something happens, and all of a sudden we have a decrease in the average particle size. And in the next slide, you will see why that happens. This is data again in Riverside. This is going from 12 p.m. to 4 p.m. and 6 p.m. The size distribution of PM in that location. We have this somewhat of a bimodal distribution, one mode being around 100 or so nanometers, which is reflective of this long-range transport and advection from the source urban areas of Los Angeles. This mode decreases in concentration as the day progresses because of the increase in the mixing depth of the atmosphere. But as the day progresses, you also have the appearance of these fresher, smaller particles that are becoming more and more pronounced, certainly around 4 p.m. in the afternoon. And that's actually a product of nucleation, of particle formation by secondary formations, or by secondary mechanisms, rather, in the atmosphere, which is becoming more and more now abundant and notable in our measurements in the receptor sites of LA. Okay, so this is basically some of the things that we talk about ultrafines and their characteristics, physical and chemical characteristics. Now, I'm going to switch a little bit to some of the instruments that we developed to study the toxic effects of these particles. And this is our recently developed ultrafine concentrator for human studies. So this system actually was developed by exclusively by funding provided by ARB. And it's a larger version of similar smaller scale systems that we developed and published in previous years, also by means of ARB funding. But it's a more automated system. It's a larger scale system, and we built it for humans. So what we have here is basically an aerosol that enters through these 2 ports. We have a 0.15 micron impactor that removes all but ultrafine particles. And the aerosol enters these boxes you see right here, in which we have deionized warm water at 35 degrees Celsius. It gets mixed and saturated. Then the aerosol goes through those vertical tubes that we call condensers. It's chilled to about 25 degrees from 35. The produced supersaturation grows the particles to about 2 or so micron. Then we pass the particles through all of these little devices that we call virtual impactors. This is actually where particle concentration occurs. In each one of these virtual impactors connected in parallel, the aerosol gets concentrated up to a factor of 50 if we want. And then the concentrated aerosol passes through a series of diffusion dryers. It's returned back to its original size, and then it's drawn through the human inhalation chamber. If we substitute the human inhalation chamber with an animal chamber, we can now do animal exposures, of course, as opposed to humans. This is, if we keep the particles, this is a schematic of a virtual impactor. And these are the grown particles. If we don't, after we concentrate these particles, if we don't dry them, but we use a commercially available impinger of sorts to collect them directly into the aqueous phase, this is we can use this extract to do in vitro cell toxicology studies. And to us, this actually reflects a very novel and improved method for collecting PM for toxicology studies, as opposed to just collecting these particles on filters over a prolonged period of sampling and then extracting the particles off the filter into a suspension. We have reasons to believe, and we are working, we've published some papers, and we're going to publish even more papers on the subject. We have reasons to believe that PM properties for toxicology are substantially modified if you collect these particles on filters and then you just wash the filter off to get the particles, whereas this is a much gentler and frankly more reflective of what's going on in our human epithelial cells and macrophage cells situation than the other method of dry collection of particles. This is a characterization of our concentrator. These three data sets reflect three different minor to total flow rates. So when we say here the flow rate is 5%, that means that we concentrate 5% of the total flow. So from the 1,200 liters per minute, we have an aerosol now at 60 liters per minute concentrated and supplied into the exposure chamber. At 3.3, the aerosol is 40 liters per minute, 30 liters per minute here in this category. And the enrichment factor is inversely, it's exactly the ideal enrichment factor is inversely proportional to this minor to total flow ratio. So if this is 5%, the ideal enrichment would have been a factor of 20. And one of the things that you see here is that basically our ultrafine concentrator, certainly between the range of 20 to 100 or 150 nanometers, it concentrates particles without any preferential concentration based on. The reason our data here stopped at about 0.2 or some micrometers is that for these two flow configurations as opposed to this one, we used our impactor that removes all our ultrafine particles. So we only conducted experiments for ultrafines, whereas here we didn't use the impactor and we've done experiments for the entire particle size range. But the point, basically, we should be getting a factor of 20, 30, and 40 here, and within the noise, of course, considering that these are ambient levels, we achieve that, and without any substantial distortion in the size distribution of PM. This is a characterization of our pre- and post-concentrated aerosols using Professor Wexler's rapid particle spectrometer. It's RSMS. At this point, I'm not sure what the S. I think is rapid single particle mass spectrometer. And this is different particle groups: carbon, nitrate, potassium, carbon, potassium. It's groups of single particles before, during the concentration, before the concentration, and during concentration again. And if you go through pretty much all of these different categories, you see that we don't, at least we haven't observed any substantial difference between the pre and the post-concentrated aerosols, at least for these groups that we looked at. We've also done similar experiments using a different type of spectrometer, the Aerodyne Spectrometer. These are experiments done in collaboration with Carnegie Mellon, the Pittsburgh Supersite. This is the size distributions with and without the concentrator, with is the dotted lines and without the solid lines, for nitrate, ammonium, sulfate, and organics. And again, within the relative uncertainties that are imposed on us by the variation of ambient aerosol, the temporal fluctuations of the ambient aerosol as you do your sampling, you see that basically the size distributions before and after concentration enrichment for all of these four categories are exactly the same. This is also the concentrated ambient and concentrated PAHs and elemental carbon. That this is obviously the concentrator on, and this is the ambient aerosol down here in this range. Again, you see that both PAH and elemental carbon are pretty much enriched concentration by the same factor, in this particular case by a factor of 50. And this is all very important because we saw in the last few graphs that whether we have a hygroscopic or a hydrophobic constituent of PM, whether we have a 20 nanometer or 2 micrometer particle, they're all pretty much enriched by the same level and the same factor, and so we preserve the physical and chemical characteristics of PM. Now, one of the things that we've done and published is we use the concentrator not only for toxicology studies, but we also used it in conjunction with a variety of other spectrometers to increase the signal of these spectrometers and now generate data on chemical characteristics of particles in very, very short intervals. A lot of these spectrometers are actually doing a very good job when it comes to the accumulation mode PM. When it comes to ultrafine PM, because of the concentration of these particles are very, very low, and because of that, there is apparently problems with the spectrometers in terms of the detection of ultrafine particles. They need a boost in their signal, and that's where we came in, and we've done a variety of studies where we increased the sensitivity of these instruments by having these instruments being preceded by our ultrafine concentrators. I'm going to just describe very briefly some of the studies that we do at Riverside with Professor Zeman. We have his thermal desorption particle beam mass spectrometer, which measures organics. We're very interested in organics, and we used it preceded with one of our concentrators. We enriched the aerosol ideally by a factor of 50. All of the particles, fine and ultrafine. And we've done some measurements in Riverside at USC during the winter and summer. We haven't finished this. These are ongoing studies, but so the summer period hasn't been covered yet. It's about to commence. We completed the winter study results, and this is some of the spectra that we saw in ultrafine PM in Riverside. This is accumulation mode PM, and most of the spectra that you see here are suggestive of composition that is rich in alkanes and hydrocarbons. Whereas when you look at ultrafine, which is these two panels, we see mostly organic acids, so more polar things in the ultrafine mode than we see in the accumulation mode. And to our surprise, we also saw a sizable ammonium nitrate signal in the ultrafines in Riverside, something that you normally don't see when you collect ultrafines on impactors and filters, because these ultrafines would be lost by volatilization, because ammonium nitrate is actually very volatile. But when you use a spectrometer like this, you do capture the signals. We also developed an instrument to measure not just ultrafine number, but also ultrafine mass concentration, because a lot of the data that Professor Freunds will describe in a minute suggests that it's also the ultrafine mass that is appears to be, because of the chemical composition of these particles, very important. So what we did is basically we took a beta attenuation monitor, it's a standard BAM monitor, and we developed a very, very low pressure drop, very small scale impactor that works at 16.7 liters per minute and removes all but ultrafine particles. This is the impaction collection efficiency curve with a cut point right here of about 0.15 micrometers, as you can see. So this is what the impactor does. It collects all of these particles and leaves these particles go and enter the BAM monitor. This is a comparison of ultrafine Moody microorganism impactor concentrations versus our BAM concentrations, and you actually see very, very good agreement, very highly correlated data, and the slope of this line is pretty close to unity, which suggests that we actually, we have very good agreement between gravimetrically measured and continuous ultrafine mass concentrations. This is actually very interesting data, whereby we compare the actual mass concentration of ultrafines to the mass concentration that would have been determined assuming spherical particles by means of the SMPS, which is the Scanning Mobility Particle Sizer. This is an instrument that doesn't measure ultrafine mass. It measures ultrafine particles by number. It measures their size. It assumes that all of the particles are spherical, so you convert these particles from, you multiply the number by the volume of every sphere, and this is the resulting mass concentration. These data are obtained in Claremont on during the July 4th, so this is Independence Day. And what you see here is basically that during the middle of the day right here, and particularly later on during late in the evening where we have the fireworks, we see that the BAM signal goes up and the SMPS signal doesn't. The reason for that is the next slide, which is actually very important in the context of studying ultrafine PM. Ultrafine particles, they're very, very volatile particles of this size mode, so the ones that are below maybe 20 or 30 nanometers are perfect spheres, because they are in fact produced by condensation of vapors, which would make droplets, and droplets are by definition spheres. But the higher end of these ultrafine particles, which would affect more of the mass of the ultrafine mode, look like this. They're fractal agglomerates. They have this very, very increased surface area, this sort of irregular shape agglomerate cluster structure. And so they deviate substantially from the assumption of a perfect sphere. The SMPS measures these particles and classifies them as particles of the accumulation mode because of their increased surface area. Whereas our instrument, the BAM instrument, measures these particles as ultrafine, so it measures the true mass. And actually make use of this discrepancy right here. They increase, sometimes, increase a signal of the BAM versus the SMPS, to come up with ways of determining perhaps the agglomerate fractal fraction of ultrafine particles. A higher, and this is a plot at USC, of the BAM to SMPS ratio would mean that we have more and more fractals in the atmosphere. Here is the diurnal plots of this ratio of BAM to SMPS at USC, with of course the ideal value being 1 if these particles are spherical. And you see that basically, and also I've included, in this, the triangles here are the elemental carbon concentrations. You see that as we go towards the early morning traffic hours, elemental carbon peaks, and so is the signal of the BAM. So all of a sudden we have more and more fractals in the atmosphere, more and more agglomerates. The SMPS cannot read them, but the BAM can. Then in the middle of the day, things tend to go down. We have more aged particles, they get closer and closer to the spherical assumption. And then in the evening, we start having a little more contributions of fractal PM that are direct products of incomplete combustion in the atmosphere. So we are using this ratio creatively to come up with the fractal content of ultrafine PM in the atmosphere. We also developed a very high volume, very low pressure drop collector to separate this time. Normally when people think about high volts in our business, they think about instruments that separate the fine from coarse PM. This is essentially a high volt dicot that separates the accumulation from ultrafine PM. And we developed this instrument. The sampling flow here is about half a cubic meter per minute. It's actually 0.55 cubic meters per minute to be precise. It's been published. And we have this instrument such that it separates the accumulation from ultrafine PM. That's where the aerosol comes in through this port, and then particles are accelerated through those 10 slits that you see right here. Accumulation mode particles above 0.1 micron or so are being collected on the strips, and right behind those strips we have a 8.5 by 10, like a filter essentially of whether it's quartz or Teflon, depending on the chemical analysis we want to do. And we collect both the strips and the filter, and we do chemical analysis in very, very short time periods, do bulk analysis to determine the chemical composition of ultrafines. This is just the characterization of our impactor. Let me skip this, because I don't think it's that interesting. I'm going to show you how we use this technology. We used it in a series of pilot studies that we just started last summer. To see how, for example, the contributions of organic compounds that are used as tracers of specific sources, how they vary from source to receptor sites over the course of the day and between the accumulation and the ultrafine mode. In particular, we looked at 4 compounds, hopanes, that are signatures of vehicular emissions without any differentiation at this point on diesel versus gasoline. That's a very complicated, actually, issue. We looked at cooking, cholesterol rather, as a function of cooking, levoglucosin, which is wood smoke tracer, and 1,2-benzene dicarboxylic acid, which is a signature of photochemistry at USC and UCR at Riverside. This is hopanes at USC and Riverside in the summer versus winter. So this is, if you go this direction, you go from the warmer to the colder season. If you go this direction, you go from source to receptor. And one of the things that is actually striking is that most of the hopanes are partitioned in the ultrafine mode, as you can see with the predominance of the red bars versus the blue bars, which would be the accumulation mode. Also, not surprisingly, at least at USC, the highest peaks are somewhat corresponding to the traffic hours, certainly in the morning and maybe one late in the afternoon. In the summertime, the interesting thing about Riverside is that the highest concentration is in the middle of the afternoon, not so much because of photochemistry. There is no photochemistry that produces these compounds, but because of long-range transport. You don't see this in the winter. You basically see, even in Riverside, one large peak in the morning. Same with USC. You basically see higher concentrations in the morning and the late afternoon hours. You also, again, you see higher concentrations in the ultrafine modes, and as you would expect, also higher concentrations at USC compared to Riverside, because USC is more affected by vehicular emissions, being an urban downtown area. I'm going to also show you the results on Silic acid in particular that we looked at. This is, again, a signature of photochemical activity. This time we have higher concentrations in the accumulation mode, as indicated here by the blue bars, although the concentrations in the ultrafine mode are still sizable. They're about at least 30% or so by mass, in some cases even closer to 40% of the total contribution to the PM2.5 concentrations of dicarboxylic acids. We see higher concentrations in both locations in the summer, as you would expect compared to the winter, because that's where we have photochemistry. But to our surprise, we actually don't see in the summertime a substantial difference between the source and the receptor side, which tells you that actually photochemistry also happens in source sides too, in Los Angeles, as you would expect, because we have sunshine there too. It's just that here we also have vehicular emissions, whereas here we don't. But if you look at these concentrations, there isn't really a whole lot of difference between SC and Riverside. This is now I'm going to switch gears and talk a little bit about our studies whereby we measure characteristics of PM and copollutants in the proximity of freeways. These results have been published now in 3 papers with Yifeng Zhu being the prime author from UCLA. This is black carbon measurements in this graph plotted versus distance from a freeway between in a freeway that is more and less affected by diesel traffic. The 710 is more, the 405 is less affected by traffic. In the 405, we have less than 5% diesel trucks. In the 710, we had about 35% diesel traffic. And you see here that basically 2 things. Well, of course, as you would expect, the concentrations decay exponentially as one moves away from the freeway. And of course, there is much more black carbon in the freeway impacted by diesel traffic than the one that it isn't. This is just particle counts and going up and down with number of vehicles. One of the things here, that's in the 405. In addition to seeing how well they track each other, one of the major features of this graph is that, and it's counterintuitive actually, is that as the number of cars decreases, which is a sign of decreased speed, more traffic, so does the number of particles. So, and this is a counterintuitive result in that people think that when you sit through traffic, you're exposed to higher concentrations. For the most part, you are, per se, as opposed to, let's just say, an urban site. But what actually puts a lot of particles out in the atmosphere is acceleration, not slow down and braking, which is really what you see right here. It's not an obvious result, but we've seen it so many times and in more experiments that I'm going to describe later on in experiments are actually done by Dane Westerdahl, that we now have reasons to believe that this is a consistent result. It isn't just one observation. This is the number of particles in different size ranges decreased from a freeway. This is a 710. One of the most striking features here that you're going to see is that the decrease primarily occurs in these very, very, very small particles. The 25 or so nanometer in size. The rest of the particles seem to be decreasing actually less, in a less pronounced manner from the freeway. This is actually the more volatile component of ultrafine PM. Winter versus summer. This is 710 size distributions in different distances from the freeway. This is perhaps, it's somewhat of a complicated graph, but if I may walk you through this graph for a second, it might become a little more obvious. What you see in the summertime, and this line is, probably the one that corresponds to 17 meters from a freeway, is that you have a lot of particles that peak around 10 nanometers. There is another peak at around 20 nanometers, very, very high number concentrations. And as you start moving away from the freeway to, 30, 16, 19, so forth meters, these particles disappear completely, and the aerosol grows a little bit inside towards the 60 and 70 nanometer range. That's summertime. The wintertime, all you basically see as you move away from the freeway is just a decrease overall in the number concentration, but you don't see any growth from this mode right here to larger size range that you see here. We have less mixing in the winter. We have less agglomeration. So in the winter, what you see basically is just a pure atmospheric dilution effect. Things decrease as you move away from the freeway because there is atmospheric dilution, but there is no mixing. And so, you don't have an agglomeration and growth of these particles as you move further away from the freeway. Again, this is also very, very important to keep in mind that the difference in summertime in the particle size ranges that actually drive the number concentrations of ambient PM. You see that in the wintertime we have much, much higher number concentrations than in the summertime of these particles, because again, remember that these particles are volatile. They are products of condensed vapors to form particles. You see that in the wintertime, and this is actually, mind you, wintertime and summertime in Los Angeles, which are defined as, 18 and 23 degrees Celsius respectively. This results in Chicago, Minnesota would have been obviously much, much more pronounced. But even in the winter here, you see that we have a factor of 3, 4, maybe 5-fold higher numbers of particles in roadways than we have in the summertime. This is also one of the reasons why in the summertime we see this agglomeration effect. You see that the surface area of PM during the summertime is almost 4 or 5 times higher than the surface area of ambient PM in the winter. The importance or the significance of that lies in that when there is a large surface area available in the atmosphere, that surface area essentially eats up the organic vapors and prevents nucleation, prevents the formation of newer particles. So you have lower concentrations in the summer because there is an ambient mass of particles already available to absorb these vapors, these excess vapors, whereas in the winter time there isn't. So you have the formation of PM by nucleation. I wanted to sort of take a couple of minutes to talk about an extremely important study that ARB has done, and we collaborated with them through our particle center and Supersite. The protagonists of that study, at least from behalf of ARB, are Dane Westerdahl, Scott Fruink, and Bowers, and Steve Mara. They developed a very, very nice unit. It's an electrical vehicle borrowed by Honda, I believe. What is it today? Whoops. Okay, by Toyota. I'm sorry. I'm not being paid by Honda. But this is a zero-emission vehicle that in which we put as many aerosol instruments and gas analyzers as we could possibly put. It's actually amazing that the space economy of this vehicle is unbelievable. And Dane, primarily in collaboration with other people from ARB and our staff in the Particle Center and Supersite, he very assiduously, and very patiently drove up and down a variety of freeways in Los Angeles and chased different vehicles, different seasons, trying to capture basically a signature of their emissions. And this, in the next couple of transparencies, is just going to give you sort of just a taste of some of this data, which are so abundant that now we have to spend some time to figure out how we can group them to make them, to convert them to publications. But there's been a tremendous interest in the exposure assessment community for this data. This is USC. So this line right here is basically the beginning and the end of a driving cycle, and that's reflective of an urban background. And all of a sudden now we have the vehicle entering the 710 freeway, following a smoking truck, getting away from a smoking truck, but just being still on the freeway. Getting out of the freeway for a second, getting back into the 710 freeway, leaving the 710 freeway and getting to the 110. The difference between the 710 and the 110 being that the 110, it's almost an exclusively gasoline traffic freeway, whereas the 710 has a major heavy-duty diesel traffic. And you can see, basically the results speak for themselves in terms of the differences between the urban background to the freeway sites and locations. You see that the people actually, depending on which pollutant you're looking at, whether elemental carbon, nitrogen oxides, which is the blue lines, elemental carbon, which is the purple lines, EADs are a measure of particle surface area of sorts, and I'm going to leave it right there for now. You see that the exposure level actually in here is probably at least half an order of magnitude higher than what it would be in a typical urban background. We also see once Dane gets into the 110 freeway, we see a very sharp decrease in elemental carbon as well as the NO levels, which provides further corroboration that gasoline vehicles don't emit so much elemental carbon and NO. But these levels are still, even the 110 is higher than the background. This is ultrafine counts, just counts again, USC. 710, exiting 710, re-entering the opposite ramp, and then going to Pasadena, the 110, and ending up at USC, which is the urban background. And now we actually see that the 110, which is basically that freeway, and the 710, in terms of particle numbers, are actually quite similar, unlike the elemental carbon and the NO levels. This is, excluding, of course, the case of a very old smoking truck that, it's sort of an anecdotal observation. The second important observation here being that, on average, these counts are again 3, 4, 5, 10 times, depending on where you are, those measured in an urban background site. And these, of course, these results have enormous implications in terms of human exposure to, especially to these pollutants, as one commutes, especially in Los Angeles, as one commutes for a substantial period of time of the day. Yes. the USC levels, actually, let me answer the question of Dr. Freund's. If you look at USC, yeah, the question, Dr. Freund's question was whether we were surprised that the levels at USC, which is reflective of a typical downtown urban site, were so low compared to, let's just say, the freeway, the in freeway locations, which, you know, the levels appear to be 3, 4, 5 times higher. If you look at these levels right here at USC, that's about 50 and that's about 40,000 particles per cc. By the standards of a typical urban area, these are actually very high concentrations. When I was in Boston and for my, you know, during my student years, typical urban ultrafine counts in Boston were mostly in the 10 to 15,000 particles per cc range. So actually, by the standards of a typical urban background, they're pretty high. But then they become even higher during commute. So these are not. It's these levels that are extremely high to make this actually very low. This is just some typical size distributions. It's also from Dane's experiments, in-vehicle experiments. This is a size distributions following a smoking truck, the diesel freeway, gasoline freeway, USC. And we chose to actually put these graphs in here because they illustrate quite a few interesting points. The scales, unfortunately, are not the same, so these concentrations will be actually substantially lower than the other 3 panels, the concentration you see. You see that in the urban side, you know, the aerosol is basically, it's a little more dispersed. You know, the geometric standard deviation of the size distribution is broader, which is reflective of a lack of a specific source. And the median diameter, at least by numbers, is of the 30 to 40 nanometer, consistent with the measurements that I showed you before. Now, if you go to the gasoline freeway, you see basically that there is a very, very high mode, if I can eyeball it here, between 10 to 15 nanometers, the very, very volatile particles that are produced by condensation of vapors, and we have an exponential decay of particles with size. So we basically have one strong nanometers, 10 to 15 nanometers, very small particles, products of condensation of vapors. If you look, and this of course would be an extreme, this panel is an extreme of this panel, but it illustrates the point. If you look at diesel trucks, in addition to this mode that you see right here between 15 or so nanometers, which is reflective of the condensation of vapors to form particles, we have also this residual right here that you don't see right here. So we have these somewhat larger particles on the high end of the ultrafine mode for diesel trucks, and these are products of incomplete combustion. This is basically these high fractal agglomerates that you actually don't see in gasoline engines. In gasoline engines, you have very, very high number concentrations, frankly higher than even diesel trucks, very high number concentrations of very, very small volatile PM. For diesel, you know, this distribution is somewhat bimodal. We have one peak right here, and then we have one peak right here. We have a lot of particles in the high ends, which are basically and these particles are solid. I mean, this is unburned soot, whereas these particles are just, again, condensation of vapors to form small liquid droplets. I'm going to skip all of this transparency about it, but I'm going to finish it maybe the next 5 or so minutes with a few concluding remarks in the context of personal exposure. We basically think that personal exposure to PM is two very, very significant components, an ambient and a non-ambient, which could be indoor or anything else, but mostly indoor. When it comes to, especially to regulation, the contribution of ambient sources to personal PM is obviously very important. The 3 major attributes that at least we've identified in our research so far that would modify this ambient PM component would be whether they're local, so they're affected, for example, for specific sources such as vehicles, whether they're regional, which is photochemistry as well as long-range transport, whether they're volatile versus non-volatile. The latter being very important in that, especially during the winter time, as the outdoor aerosol penetrates indoor, particles are actually gone. They're going back to the gas phase. We have shown, with respect to the local versus regional nature of PM, in the winter time, we basically have a delicate balance between dilution and condensation nucleation that explains the special trends and decays of particulate matter from the freeways. Dilution affects PM, carbon monoxide, and hydrogen oxide. Condensation nucleation affects only PM. This is extremely important. This is extremely important because it shows you that basically the trends between PM and gaseous copollutants with respect to freeways will not be the same because the nucleation and condensation process affects differentially the size distributions of these particles and the concentrations. And so these gases cannot be used as tracers of ultrafine PM for vehicular emissions, which is something that only now starts becoming more and more obvious to people in the area of epidemiology. But that's really the reason why. And I can talk more if you want about this afterwards. Some other attributes of PM in Los Angeles based on the observations that we made and over now 3.5 years of measurements. During the cooler season, which is in a lake characterized by higher humidities and lower temperatures, we have obviously higher contributions of PM due to vehicles and wood smoke. These PM tend to be more local. They're more affected by the proximity of the source, so that will increase the spatial variability of PM. We have a much higher concentration of PM in the winter. We have much higher concentration in urban areas and lower concentrations in receptor sites. And overall, the PM is finer in size. It's towards the 0.3 or so micron size range with an increased ultrafine component. And that finer size, of course, has implications in terms of the penetration of PM indoors, as well as, of course, dosimetric implication, where these particles deposit. And of course, another unrelated to PM, but related to our habits, during the winter time, we spend less time outdoors, and of course, PM infiltration rates of PM are lower. In the winter time, the warmer season, not the winter, in the summertime, we have decreased secondary formation, we have increased long-range transport of PM. Both of these two mechanisms tend to actually disperse and distribute PM very nicely, homogeneously, especially in receptor areas. We have overall higher accumulation mode, and of course, we also spend more time outdoors, and in the absence of air conditioning, we have more PM. These are all very, very important components in putting all of this picture together and translating all of our outdoor measurements into personal exposure. From a regulatory standpoint, effective protection of public is by definition reduction of the mobile source, or not the mobile sources, but actually the sources that would be mostly responsible for having a sizable contribution to personal exposure. And this actually could be, this could become an important, a significant problem to solve, but there have been advances lately in the area of molecular tracers, an area that, the late Glenn Cass started, quite a few years ago, and now, he conveyed, before he died successfully to his doctoral students who are now on the faculty of other universities. They've done so much work on identifying species, organic tracers like those that I showed you a few slides ago that are associated with specific formation mechanisms, that this use of molecular traces can now enable us to apportion sources and formation mechanisms if we combine those with personal PM monitoring and determine the degree to which these sources contribute to personal exposures, how these personal exposures depend on season, proximity to source, home characteristics, and individual activity patterns. And of course, these molecular tracers, if we use them ideally with panel studies as well as toxicological studies, may be extremely informative and invaluable in enable us in the end to find out what sources would be more responsible or formation mechanisms for health effects. So I'm going to stop right here, and thank you, and I would like to. Does anyone have questions? There's no questions. I guess we'll conclude.
I think we've got time for questions. Any questions? So we need people to ask questions first.
I'd like to make one comment. I just want to emphasize something Kostas said, which is the line before the bottom, ideally concurrent with panel studies as well as toxicologic studies. I think we're at a place now where we think panel studies are particularly important. One of the problems with the children's health study is that it's enormous in scope. And some of the problems we found in some of our human clinical studies is very small sizes of participants. And so we think we need studies with a reasonable N value where one can really test toxicologic hypotheses. And so the panel studies are at this point becoming important ways to test biological and chemical hypotheses as well as obviously aerosol issues.
That's a very nice presentation, Costas. I was very interested in this idea of the different instrumentation that lets you look at fractal forms.
Yeah.
And I'm wondering, what does that mean? Do you have any thoughts about, perhaps aerodynamic characteristics or deposition patterns that may influence the toxicity of these chemicals, I guess, based on their surface characteristics or their morphology?
Well, of course, whatever I'm about to say, I need to preface the statement by saying that it's completely speculative, because we really haven't done any studies whereby we see or determine whether the enriched in fractal fraction ultrafine PM affect differentially a toxic outcome. These studies, this would be extremely interesting to do, and in fact we are now in a position to do it, and we plan to do it. Starting this year with the ultrafine human exposure studies that we're doing at Rancho Los Amigos with Henry, we're going to be measuring also the fractal content of PM as these people are breathing ultrafine particles. They increase the odd and sort of cluster agglomerate structure of these ultrafine particles, I believe, has several implications. First of all, it has a very high surface area and a mostly carbonaceous composition, which probably makes these particles very, very effective sorbents of organic vapors. So they're very, very nice sites onto which organic molecules in the vapor phase can go and sit, as opposed to just a spherical particle. It probably also affects the site in the respiratory system where these particles deposit, because particles in the respiratory system, especially in the ultrafine mode, don't deposit so much based on their aerodynamic, but mostly on their mobility diameter, on the surface area diameter. So we have reasons to believe that, yes, this is actually an important property to measure if one could measure it. It's not an easy thing to measure directly, and every method that we have so far is somewhere, the only direct method would be obviously do microscopy. But that, there are issues about it, how to do it, and how you can sample effectively over a course of 3-4 hours, get different slides and look at them under a microscope. But it's something that, have probably one of the most eminent faculty in air pollution, Professor Friedlander, looking at the issue of how he can actually develop methods to measure the fractal agglomerate content of ultrafine PM. But this is something that, I do suspect that will have implications toxicologically for at least the two reasons that I gave you, and something that, if we could, we should measure.
Just to follow up from a toxicologic side, Kent, we think that this finding of Costas's and Friedlander is really very important from our standpoint, because we think that elemental carbon is not benign. We think it is a very, very strong electron transfer medium. And so if one is interested in what I'm going to talk about this afternoon, oxidative stress, then it's our view that the elemental carbon acts as an electron transfer agent. Those fractals that he showed become even more effective than a spherical species.
And add on to what Dr. Freund said, we also have very strong evidence based on our DTT measurements that I hope you're going to talk about, where we see a very strong correlation between the rate of redox cycling and the elemental carbon content of PM. So, over
here. So I have a question. So I saw your spectrum. There is a huge peak on the 149. Looks like a phthalate. So I just wondering, is it a phthalate or some lab contaminations?
I think let me go back to this for a second. I think Professor Zeman made a similar observation too. I think it's coming, I'm sorry. There we go. This one.
149.
The 149, I think this particular compound actually some contamination to pick up from the lines, from the sampling lines. I think that's because I asked the same question, Professor Zimmer, and that's the interpretation that he gave.
Oh, okay. So another question. So when you talk about the source, I saw one article from South Korea. They're talking about the global factor. So I just wondering. So do you think about the global factors?
By global factors, you mean like on global climate and things of that nature, or
yeah, from another country. The source from another country.
Oh, so long, even much longer range transport that we. Well, it's hard for me to tell you at this point that the whatever transport you might have in Los Angeles with respect to especially the finer range of RPM 2.5 may be substantial compared to the unbelievable local sources that we have, which is the vehicular emissions and/or. I don't think we've done, and I'm not even sure how would one go about doing these kinds of studies to examine long-range transport from the Pacific, for example, in LA, and what would we be looking for, how we distinguish that. But we have reasons to believe that the emissions that we have from LA are such, especially considering the number of cars and of course the photochemical component of our mechanisms, that are so overwhelming that I can't believe that we will have a substantive or substantial contribution from.
Yeah, one other last question is that when we were measuring coastal air, we got ultrafine particle counts as low as 600 counts. So
right. Which
600 is not going to make much of a difference in terms of when you're talking about 50,000 or 100,000.
Of what you just said, that you wouldn't expect to have a substantial contribution from, advected particles other than the ones that are produced in LA.
There's a lot of dilution that goes on.
Yeah.
The other point real quickly is, and we'll talk about it some other day in detail, the one measurement we have that's related to fractals would be the EAD measure.
Yes.
And it basically measures something about the particle length.
Although it's still, and more of this discussion, I don't know how many of you.
It relates to the carbon measurements really well.
We're going to have more discussions on nanoaerosols and measurements in a workshop at UCLA next week, Friday and Saturday, which is organized by NSF and is co-sponsored by our center. And this is one of the things that will be discussed actually, ways to measure fractals, surface area, whether things like VAD, which is basically focusing on diffusion charging of these fines, whether this is an appropriate mechanism to measure the surface area of ultrafines, and what other ways there are out there to determine this property.
We have two questions from the one is from Martin Rubin from earthlink.net, and he's very concerned that the content of jet fumes is not being seriously looked into, and he was wondering if our two speakers would consider doing such a study.
Well, we haven't talked about whether we're going to do a study in the proximity of airports. It probably is a very good idea. We have recent measurements, again, done using this ARB vehicle, in particular Dane Westerdahl, that he has looked at the contribution of jet fuel engines to the overall urban ultrafine PM. And Dane, you want to say something about this? I know this is mostly very fresh, very preliminary data, but is there anything noteworthy about these observations that you made?
Well, a couple things is that jet fuel isn't exactly like diesel fuel, and many people have been trying to find how to differentiate the two. Jet fuel, as I understand it, doesn't have it's more refined than diesel fuel is on average. I could be wrong about that, but that's what I've been told. But we did do some monitoring just upwind of the freeway, just upwind of the airport at LAX, next to the airport at LAX, and then downwind and immediately downwind of airport operations at LAX. And it definitely, LAX has a pretty strong impact on the local and even regional, I think, air quality in terms of ultrafine particles. The operations are complex at airports because there are vehicles around, there are cars around taking people back and forth, tow vehicles, as well as the ground and air operations of the planes. But you can clearly see an impact in terms of particle numbers and particle, and especially of small particle size when jet engines take off and land. Sometimes very huge numbers, in fact, of particles when airplanes take off.
The COSIS don't know this, but we have one investigator at UCLA who has been very interested in this, and he's been working with two modelers, and they have done some modeling and some calculations of emission factors and actual amount of ultrafines that are produced when a plane takes off and lands. And when you look at the numbers, they are striking. And so it's clearly an area that deserves attention. And I was a complete skeptic. I went into this meeting thinking, God darn it, I don't want to spend an hour talking about airplanes. And when I walked out, I was convinced that we need to, at least to the degree that we can, take a look at this further. The numbers are enormous.
My question is about fractal fraction of Pm. It went by pretty fast, so I'm not sure if you addressed this already, but I'm looking for my question. You said something about the size and the nature of the particle affects how it deposits in the lung.
Yes.
And how would you characterize the spherical deposition versus the fractal fraction?
How would I characterize it? I'm not sure that this is. I mean, if you're talking about doing real-time experiments where we measure the deposition of these particles, there are ways of doing it. But if you ask me how would a particle that has the same mass, but it's hollower and has a higher surface area, would deposit in the lung versus a smaller spherical particle with the same mass but much smaller surface area. And for the sake of hypothesis, let us say if these two particles are the weight, they're perfect. One is a perfect sphere, the other is a fractal. The perfect sphere is 50 nanometers. The fractal is, well, whatever it is. It looks like this, right? My hypothesis is that the fractal particle would deposit probably in the upper airway a lot more effectively than the smaller particles that would penetrate into the deeper lung. No, because the notion of ultrafine Pm having a substantial component of them that consists of basically these fractal agglomerates is very new. But it's certainly extremely worth studying. Yes.
Okay, we got one last question off the web, and I think we got to call it a day. Right.
We have a couple of requests. Your PowerPoint presentations that's okay?
Sure.
All right, we'll make sure it's up there. And for the people that are watching, we'll post the link as well as soon as possible.
Okay. I think we'll kind of end it there just because we need to take a break. And I want to thank Dr. Siutis. And we'll be back about 1:30 to hear Dr. Freund's and the toxicological implications of the particulate pollution. Thank you.